Okay, so one more example here in 9.3 to finish off this solving technique for linear differential equations. Here we go. This one has an interesting element here right at the beginning. xy prime minus y equals x natural log of x. Okay, so it turns out this is a linear differential equation, but it's not quite in the right form yet. We don't want to start to find an integrating factor the way it's written. If you will recall, a linear differential equation looks like y prime plus f of xy equals g of x. And with this x in front, we don't just have y prime plus f of xy. So the first thing we need to do is to make it look like it should. If we were in class, I'd say, hey everybody, what should we do to both sides to make it take the correct form? And let me even just, I've said it in words, but let's write it out again. It must be put in this form. So what should we do to each of the terms? And if you said we should divide them all by x, then you got it. Divide both sides or divide each of the three terms by x, and that will give us the form we want. Y prime minus 1 over x times y equals the natural log of x. And now we can clearly distinguish f of x and g of x. Be really careful also, f of x, if I can write it, f of x includes that negative. Gotta need that too, because we always think of it as being added. Okay, of course, the g of x, you know, it's really the f of x that we need to be careful with to start things off. So we're gonna find our integrating factor. We'll take f of x, take its antiderivative, put it into the power of e. Okay. Now this one's kind of neat. It's negative natural log x. Now here's another interesting feature for this example. Our integrating factor involves the natural log of x, e to the negative natural log x. And we know that e and natural log cancel out. We want to make our integrating factor as simple as possible. Remember, we're going to end up multiplying this by g and then having to integrate. Well, the way it looks right now, I don't want to multiply it the way it looks right now by g and have to integrate. I'm not going to be able to do anything with that. I need to simplify this. You're like, well, yeah, sure, e and natural log cancel out, but this negative is there. This negative is like in the way. I can't cancel them with that negative there. You're absolutely right. There's something that we can do with that negative. If you remember from algebra, some of the rules of logs, if there's a coefficient, we can move this up as an exponent on the x. So we're going to rewrite this as e raised to the natural log of x to the negative 1. And now the e and the natural log cancel out. Our integrating factor is x to the negative 1. Or actually, that would probably be fine. But I'm even going to go a step further and say that it's 1 over x. Then that's really going to let me do my integrating later a little bit more easily. Either one of these would be okay, but yeah, that one's just slightly bit better. All right, so I'm going to take my integrating factor. And do you remember what we should do with the integrating factor? Well, if we were in class, maybe you would tell me, but since I'm just here on my porch, we're going to take our integrating factor and we're going to multiply it back by each of our terms, like so. So when we do that, we've got 1 over x y prime minus 1 over x times 1 over x. Y equals the natural log of x times 1 over x. Our integrating factor multiplies to each one. And let's clean that up a little bit. I'm going to write it this way. Okay, so we found the integrating factor. We've multiplied it to each of our terms. This continues for me on the next page. here's the next step. After you've multiplied your integrating factor, maybe you know by now, we've done it a couple times, talked about it a few times, that's the answer to a product rule. And it's always the product rule of your integrating factor times y. So we're going to write d over dx, the derivative of 1 over x times y, is equal to, and well, this is just an equivalent statement, so all we do is copy there, the natural log of x over x. Now I encourage you, if you're ever not sure of yourself, hey, go ahead and perform that product rule. Confirm that you really do get that left side up above. Or if you prefer to just trust me, I mean, I've said it a bunch of times, but always your integrating factor times y. Okay, so what do we do at this point? Now that we have this as a derivative, if we simply integrate both sides, we can cancel that out. And that's what I'm going to do. Integrating here cancels out my derivative. Boom. Equals this integral with respect to x. And if I can get this integral, then I'll basically have the answer. So let's see. Integrating there, well, what technique do I need? A u substitution. We can make u equal the natural log of x. So du is 1 over x dx. Oh my gosh, it just falls perfectly into place. That's amazing. So using that u sub, integral of u du, that must be 1/2 u squared plus c. Put your natural log of x back in. And I know I'm going rather swiftly, only because I expect people to be really familiar with u substitutions at this point. Okay, so we put the u back in. 1 over x times y equals 1/2 the natural log of x squared plus c. We want the explicit solution always in a linear differential equation when we solve. All we got to do is multiply everything by x, and we'll have it. When you multiply by x, it multiplies right there, and it multiplies by c, and you probably caught me. I just filled that in. I forgot to do it earlier, but I remembered in the midst of explaining it. Isn't that cool? So multiply by x, your arbitrary constant needs to get multiplied by x because now it's a constant times x. There's your explicit solution to this differential equation. Okay, in the homework, obviously you're going to be doing this technique for everything. You might have to rearrange the equations, at the beginning, right? Like we did here, we had to divide everything by x before we got started. So be on the lookout for those. Also, we didn't do any examples here in the lecture, but you can certainly have questions that ask about particular solutions. And so you might find a general solution, and then you might take it a step further by finding a particular solution at a certain initial condition. I just wanted to focus on the new technique in this lecture, and to keep it a little bit shorter. And we did the particular solutions back in 9.1 and 9.2. Okay, so that wraps up 9.3. Next, in 9.4, we do the applications. We're going to do applications of separable equations and linear differential equations. We got 2 applications of each. See you then.